Hey! How you doing? I'm back again. This time we are looking at lesson 1.6c, limits at infinity. Wow, that seems interesting. Limits at infinity. All right, well, let's see, Mr. Wright. When we talk about limits at infinity, we are referring to, in essence, horizontal asymptotes. Infinite limits dealt with the vertical asymptote. However, limits at infinity, okay, we're talking about horizontal asymptotes, which you learned in pre-calculus and in Algebra 2. So I'm not necessarily going to look at the pre-calculus and Algebra 2 approach for the most part. We will look at a little bit, but we're going to do both. Calculus approach and some of the Algebra 2 pre-calc approach as well. All right, here we go. Very quickly. Here are the three possibilities you learned in Algebra 1, Algebra 2, and pre-calc. Okay? If n is greater than m, if n is less than m, and if n equals m, and these are the powers related to our problem, the exponential power. All right? But I want to jump right to the calculus of it. Please remember to divide the numerator and the denominator by the highest power of x in the denominator. Of course, we'll talk more about this in class, but we're trying to get to the example so you can work your way through that. Okay? And I'll explain it, of course, as I do the problems. All right? That's critical. For example, here we go. Example 1. Let's go after it. The limit as x approaches infinity of the quantity 5 minus 2 divided by x squared. All right? First things first. All right? 2 over infinity squared. This fella here approaches 0. That's the point. 2 divided by infinity squared approaches 0. In other words, no matter how large the number is, x can approach very large numbers, like 100. If you have 2 over 100 squared, that number is getting close to 0. Okay, let's say x is approaching 1 billion. If you have 2 divided by 1 billion squared, ladies and gentlemen, that is a very small number. So the larger x becomes, the smaller this value is. And it gets small very fast because x is being squared. So this approaches 0. So this is going to equal 5 minus 0, which is 5. Okay? Let's move on. Example 2. Now, we said you ought to multiply every term by the highest power in our denominator attached to the variable. Well, the highest power in the denominator here is x to the power 1. So divide everything through by just x. Let's divide everything by x. So this is going to give me 2 over x divided by x minus 1 divided by x all over x divided by x plus 1 divided by x. I divided everything through by the highest power in my denominator. Okay, in this case it's x to the power of 1. All right, what is it equal? The x is canceled out, so I'm going to have 2 minus 1 over x divided by x over x is just 1 plus 1 over x. And now go back and grab infinity. Go back and grab infinity, substitute in for x. Okay? And so, if we were to write 2 minus 1 over infinity divided by 1 plus 1 over infinity, well, we know exactly where this goes. This goes to 0. Because 1 over a very large number. 1 over a billion, that's close to 0. 1 over 5 billion, 0. So this goes to 0. So I'm going to have 2 minus 0 divided by 1 plus what? 0. That equals 2. And you're done. Let's go back to algebra 1, or algebra 2, pardon me, algebra 2. Because a few moments ago we had on the board n less than m and n greater than m and all that kind of whatnot. What that was referring to from algebra 2, you learned this. If the powers of x are the same, x to the power 1, x to the power 1, in other words, if you have the limit as x goes to infinity of 2x to the power of 1 minus 1 over x to the power of 1 plus 1, if the two powers are the same, if the two powers are the same, then the limit is going to be the coefficients. The answer is going to be 2 over the coefficient right here, and this coefficient down below here is 1. That's your answer. 2 over 1. And 2 over 1 is 2. And it's 2 over 1 because the powers of x are the same. When the powers of x are identical, the answer will be the coefficients. Okay? It's the coefficient. In fact, it's the quotient of the coefficients. 2 divided by 1, which is just 2. So, I could do it this way, which is the upper level calculus pre-cal way, or recall what you learned in algebra 2, which is this way right here. Look at the powers. Look at the powers and go right there, right to the answer. All right, let's go. Okay, what's next? Wow, look at that. Oh, wow. All right, so we'll do it the pre-cal way, and then we'll come back and grab algebra 2. All right? Well, you have power 1 right here. Well, what's the greatest power in the denominator? X what? What'd you say? Oh, I thought you said that. X squared? Correct. Divide every term by x squared. 2x divided by x squared. Plus 5 divided by x squared. Over 3x squared divided by x squared. Plus 1 divided by x squared. Equal. Well, here I'm going to have 2 over x, because of x squared I'm going to lose. 2 over x plus 5 over x squared over 3, because the x squares here cancel out, right? So I have the 3 left over. Right here, I have an x left over down here, and this x goes away to 1. That's why I have 2 over x up top here in my numerator, plus 1 over x squared. We're almost there. All right, so what must we do now? Now we have to look at what happens as x gets very large. As x grows and x becomes large, what values do we get? As x becomes large, 2 over x becomes what? As x gets very large, 2 over a very large number approaches what? That's right, 0. This approaches 0. Plus, this also approaches 0. 3 approaches itself, 3. And 1 over x squared approaches 0. So I have 0 plus 0 over 3 plus 0, which is 0 over 3, which equals 0. So that limit is 0. Pre-calc. Let's go back to Algebra 2 for a moment. Algebra 2 says, okay, look, if the power here is a 1, and the highest power in my denominator is 2, then the horizontal asymptote is just going to simply be 0. That's it. All right? So this limit is 0. And that's it. Well, oops. That's the null set. It's not the null set. It's 0. And why is it 0? It's 0 because the highest power in my numerator, 1, is smaller than the highest power in my denominator, 2. If the smaller power is on top or in the numerator, and the larger power is in the bottom or in the denominator, then the limit is 0. My horizontal asymptote is y equal 0. Okay, good. Let's go. This is very easy. We know the answer already. Are the powers the same? Well, if the powers are the same, what do we say the answer is? What do? We just did one like this maybe 2 or 3 problems ago. The powers are the same, we take the what? Start with a C. No, not constant. Take the what? Coefficients. Good, coefficients. So I know my answer is going to be 2/3. Why? Because the powers are the same. Yay, 2/3. Let's prove it using pre-calc. Let's go. So divide everything by the highest power in the denominator. So 2x squared, well, divided by x squared, plus 5 divided by x squared, all over 3x squared divided by x squared, plus 1 divided by x squared equal. You do not have to do all of this, but it's good to know it. Well, the x squares cancel out. Go to 1. So I have 2 plus. Where does 5 over x squared go? That goes to what? Good, 0. The x squares cancel here. I have 3. Plus, where does 1 over x squared go? 0. Ta-da! Answer, 2/3. All right. Wonderful. Let's get on down the line here. Example 3. Well, now we have to divide everything by the highest power in our denominator. Okay. 2x cubed divided by x squared plus 5 divided by x squared all over 3x squared divided by x squared plus 1 divided by x squared. It's going to give us, start canceling, the x squared canceled. I'm left with an x right here. That's going to give me 2x. Plus, where does 5 over x squared go? 0. The x squares cancel, go on to 1. I'm going to have 3 plus, where does 1 over x squared go as x gets large? 0. So I'm going to have now 2x over 3. The limit as x gets very large. What does that equal? Well, in this case now, as x gets larger and larger and larger, if I multiply it by 2, wow, imagine that. Imagine x being 1 trillion. 1 trillion times 2 is 2 trillion. 2 trillion divided by 3 is still what kind of number? Very large. Very large. It's a large number. And so the point here is, no matter how large x gets, or x becomes, this here, this expression here gets larger. It also gets large. It also expands. It's also not bounded. It's unbounded. So it goes to infinity. It's unbounded. There's no cap on it. It does not approach a what? Value. It does not approach a value. Okay? So this limit does not exist. It's follows infinity. All right. Good. Oh. And the Algebra 2 method tells us that if the numerator, if the power in the numerator is bigger than the power in the denominator, if the numerator power is larger than the denominator power, then there is no horizontal asymptote. No horizontal asymptote exists. That's it. This right here, ladies and gentlemen, is what we call a slant asymptote. It'll have a slant asymptote, not a horizontal. Okay, so this is going to give me a slant asymptote. A slant asymptote that's linear. A slant asymptote that's linear. How do you know it's linear? Because in the word linear is the word line. All lines have power 1. What's the difference between 3 and 2? 1. Line. If this were the power of 4, the difference between 4 and 2 is 2. So now we're talking a quadratic slant asymptote. And so on and so forth. Okay? All right. Very good. Limits at infinity involving trig functions. Trig functions. Okay? And so, as we go out into infinity, as x becomes infinitely large, what value does sine x approach? That's the point, in essence. As x becomes infinitely large, what value does sine x approach? Well, let's see. Okay, 1, -1, sine wave. Notice that the sine wave, no matter how far we go out along the x-axis, and it just keeps going and going and going and going, the sine wave, its approach oscillates between 1 and what? -1. It goes up as high as 1, down low as -1, then back up to 1, then it's going to go back down to -1. So as we go, as x travels toward positive infinity in this direction, the wave goes 1, negative 1, 1, negative 1, 1, negative 1, 1, negative 1. So this limit right here does not exist. Because it keeps going back and forth. The further out you go, it just goes back and forth between 1, negative 1, up, down, you know, like a carousel, you know, up and down, up and down. So it doesn't exist. It's not a bad thing to go up and down. It's like, you know, when you're in the hospital, the EKG, it goes up and down. That's good. That means you're still alive. That's okay. Okay. That's like life. You have your ups and you have your what? Downs. But you're all right. Anyway, this limit doesn't exist. All right, let's go. Okay. All right, now let's look at the limit as x approaches infinity of sine x over x. Now in this case, we have to use what we learned a few lessons ago called the squeeze theorem. All right, so we got to squeeze this particular situation here to see where we're approaching, if a value at all. If we are approaching a value, we don't know. All right, so that's some things we have to be familiar with. First, we have to understand, you have to recall that the absolute value of sine x is less than 1. Or less than or equal to 1, really. All right? So what this implies is that all the values of sine x are sandwiched between, in the interval, in the inclusive interval, of negative 1 and 1. All the values of sine x. The sine of any angle. All right? The angles are inclusively between negative 1 and 1. So this here can be written as negative 1 less than or equal to sine x less than or equal to 1. These two are the exact same thing. Same thing. No different. Same thing. All right? So now let's use this fact. Use this fact as we now approach the problem here. Okay? All right, let's go. So let's look at this. Consider the limit as x approach infinity. Let's keep it all together. Negative 1, sine x, 1, positive 1. Positive, negative 1. But that's not what we have here. Here we have sine x divided by x, don't we? Okay. Well, let's take it a step further. Let's divide everything by x. Let's do that. So we took our fact. Our fact is negative 1 is less than or equal to the sine of x, which is less than or equal to 1. Took the fact, and now we're going to divide all the fact by everything by x. All right? And so now, let's look at each piece individually. Let's look at the limit as x approach infinity of negative 1 over x. First, let's look at this piece first. All right? As infinity, as x gets very large, negative 1 over a very large number is close to what? It's close to 0. Negative 1 over a very large number. Negative 1 over a billion. That's very, very close to 0. All right, we got that. We good. Now jump to the other side. Let's jump on this one. What's the limit as x gets very large of 1 over x. 1 over a large number, what is that close to? Let me see, 1 over a billion. 1 over a billion approaches and is very close to what value? 0. So this goes to 0, and this one over here goes to 0. So one end goes to 0, the other end goes to 0. So if my end's going to 0, where do you think the middle's going to go? Because the middle is sandwiched in between. It's squeezed, you know, squeezed in between. So if the ends approach 0, then the middle must also approach what? You got it, 0. By the squeeze theorem. Because look, this centerpiece right here is greater than this end, greater than or equal to this end, but it's less than or equal to this end. So by logical conclusion, if the left end is 0 and the right end is 0, then what's in between also has to be 0. They're all equal. So this equals 0. Probably in squeeze there. All right, have questions, ask them in class. You know, we do these series of lectures to help you get through the example problems. I'm done. Take care. See you next time.